China just cut the price of their flying car in half. Again, not from $1 million to 500,000, not from a luxury price point to a merely expensive one, from already shockingly cheap to something that is starting to make the entire global aviation industry genuinely nervous about what comes next. Because here is what nobody is saying out loud yet. The $4,937 flying car that shocked the world last year was not the bottom. It was not China showing you where the price floor is. It was China showing you where the price floor was at that moment, and the moment has moved. The manufacturing cost compression that produced $4,937 has not stopped. It has accelerated. The supply chains are more developed. The production volumes are higher. The component costs are lower. The lessons learned from the first generation of mass-produced flying vehicles are being applied to the second generation at a pace that makes the trajectory of what is coming considerably more alarming for Western aviation companies than where things currently stand. And where things currently stand is already alarming enough. Today we are going deep into the cost compression story. Not just what the price is right now, but what drives it down, how fast it is falling, where it is going, and what happens to the global aviation industry, to the concept of commercial flight as you currently understand it, and to every business model built around the assumption that flying is expensive when personal flight costs less than a decent laptop. By the time we finish, you will understand why the price story is not a footnote to the flying car revolution. It is the revolution. Everything else follows from the number, and the number keeps falling. Hit the like button right now before we go any further. This kind of research takes serious time, and every like directly helps this reach people who want the full picture rather than the headline. Subscribe and turn on notifications. This story is moving faster than most people realize. Let us get into it. To understand why China can cut the price of a flying vehicle in half while Western companies struggle to bring theirs below $1 million, you need to understand something fundamental about how manufacturing costs actually work. The price of any manufactured product is not determined primarily by the complexity of what it needs to do. It is determined by the manufacturing ecosystem that produces it, the supply chains, the production volume, the component costs that fall as those volumes rise, the accumulated engineering knowledge that reduces waste and improves yield at every stage of the process. Western flying vehicle companies are building their manufacturing ecosystems from the beginning. They are negotiating with suppliers who have never made components for electric vertical takeoff and landing aircraft before. They are developing quality control processes for a product category that has no established standards to draw from. They are training workforces in skills that did not exist as a commercial manufacturing discipline 5 years ago. China is not doing any of that. China redirected an existing manufacturing ecosystem of extraordinary scale toward a new application. The electric vehicle industry that China built over 15 years produced supply chains, production volumes, component costs, and engineering knowledge that transferred directly to flying vehicle manufacturing. The motors, the battery systems, the power electronics, the sensor arrays, the autonomous control systems. All of it developed, refined, and cost-optimized through years of electric vehicle production before a single flying vehicle came off a production line. When BYD produces a battery cell for an electric vehicle, the cost of that cell reflects the accumulated learning of manufacturing hundreds of millions of cells over 15 years. When a Chinese flying vehicle manufacturer sources a battery system for an autonomous aircraft, they are buying from that same ecosystem at costs that reflect that same accumulated learning. A Western flying vehicle startup buying battery systems is paying the price of a supplier relationship that is years younger and volumes smaller. That difference in starting position is the entire explanation for why the $4,937 price point exists, and it is the entire explanation for why the price keeps falling while Western prices stay stubbornly high. Let us talk about what the cost compression actually looks like in practice, because the abstract explanation of why it happens is less revealing than the specific numbers of where it has gone. The EHang EH216S was the vehicle that established what a certified autonomous passenger aircraft could cost at commercial production scale. When it first reached the market, the price per unit reflected early production volumes and early supply chain relationships. Over 300 units are now delivered and operating in real commercial environments. The accumulated production volume of those 300 units and the manufacturing improvements that come from building the same product repeatedly and applying what you learn has brought the per unit cost down from where it started. This is the learning curve effect, and it is one of the most reliable phenomena in manufacturing economics. Every time cumulative production volume doubles, per unit cost falls by a predictable percentage. The specific percentage varies by industry and product complexity, but the direction never varies. More units means lower cost per unit, always. China has more units in production across more flying vehicle platforms than any other country on Earth. The learning curve is working in China's favor across the entire industry simultaneously, not just within individual companies. When XPeng learned something about reducing the cost of propulsion systems for their land aircraft carrier, that knowledge spreads through the supply chain and benefits other manufacturers buying from the same suppliers. When a battery supplier develops a more efficient production process to meet demand from one flying vehicle customer, every other flying vehicle customer benefits from the lower cost that improved process enables. The ecosystem learns as a whole, and an ecosystem that learns as a whole reduces costs faster than individual companies learning in isolation. The XPeng land aircraft carrier sits under $280,000 today. That price already undercuts the cost of helicopter ownership before you factor in the pilot license requirement, the dedicated landing infrastructure, and the $100 to $300 per flight hour operating cost. But $280,000 is where the price is now. The question worth asking is where it goes over the next production cycle. XPeng is not a company operating at the margins of Chinese manufacturing capability. It is a company with the engineering resources, the supplier relationships, and the production scale of a major automotive manufacturer applied to a flying vehicle program. The factory in Guangzhou already has annual capacity for 10,000 units. 10,000 units per year is a volume that triggers significant cost reductions from suppliers who are now building at scale rather than in small batches. At 10,000 units per year, the component costs fall. The manufacturing yield improves, the overhead per unit decreases, the learning curve accelerates. The price that 10,000 units per year enables is not the same price that 1,000 units per year enables. It is substantially lower. And 10,000 units per year is just the current capacity. The trajectory of demand, measured in the 5,000 confirmed pre-orders already placed with real deposits, suggests that capacity expansion is already being planned. Demand that exceeds supply creates the business case for investment in more production capacity. More production capacity creates the volume that drives further cost reduction. The cycle is self-reinforcing and it is running. Now, the number that puts the trajectory in its sharpest context. China's Low-Altitude Economic Alliance projects 100,000 autonomous flying vehicles operating over Chinese cities by 2030, 100,000 units. The entire global commercial airline fleet numbers approximately 25,000 aircraft. China is projecting 4 times that number of autonomous flying vehicles within 4 years. What does producing 100,000 flying vehicles do to the cost of producing one flying vehicle? The answer is that it does something dramatic. The component suppliers who are currently producing at volumes measured in hundreds of units per year are operating at cost structures that reflect those volumes. At 100,000 units per year, the cost structure is fundamentally different. Raw material purchasing happens at volumes that unlock pricing tiers that do not exist at current scales. Manufacturing processes that are currently partly manual because the volume does not justify full automation become fully automated. Quality control systems that require human inspection at low volumes become algorithmically managed at high volumes. The price of a flying vehicle produced as part of a 100,000 unit per year ecosystem is not the price of a flying vehicle produced as part of a 300 unit ecosystem. The relationship between those two prices is not linear. The lower volume price does not predict the higher volume price by simple extrapolation. The cost reduction is disproportionate to the volume increase because the nature of the manufacturing process changes, not just the scale of it. Here is where the cost compression story connects to something that most coverage of Chinese flying vehicles misses entirely. The $4,937 personal flying vehicle is not the product of a company that set out to build a $4,937 flying vehicle. It is the product of a manufacturing ecosystem that got costs down to a level where a $4,937 flying vehicle became commercially viable. The price did not drive the product. The cost structure made the price possible, and then a product was designed to fit within it. This distinction matters because it tells you something about what comes next. If the manufacturing ecosystem continues to compress costs, which the trajectory of production volumes and learning curve effects suggests it will, then the next price point is not determined by what a company decides to charge. It is determined by what the manufacturing ecosystem makes viable, and the manufacturing ecosystem is not making decisions about price. It is following the iron logic of volume, learning, and scale. Where does that logic lead? The electric vehicle industry provides the most relevant reference case. In 2010, the cost per kilowatt hour of lithium-ion battery cells was approximately $1,000. In 2024, it was below $100, a 90% cost reduction in 14 years driven entirely by manufacturing scale, learning curve effects, and supply chain development. Not by any single breakthrough technology, by the compounding effect of making more of something and getting better at making it. Flying vehicle manufacturing is following the same trajectory at a pace that reflects both the head start that electric vehicle manufacturing gave it and the additional learning that comes from a 30-plus company ecosystem all improving simultaneously. The $4,937 price is not the floor. It is a point on a curve that is still declining. And the curve has not yet reached the part where the cost reduction really accelerates, which is the part where production volumes hit the thresholds that change the nature of manufacturing, rather than just the scale of it. Now let us talk about what falling prices actually mean for the world beyond the flying vehicle industry itself. Commercial aviation, as it currently exists, is built on a cost structure that assumes flying is expensive. Airlines exist because individuals cannot afford to own and operate aircraft. Airports exist because aircraft need expensive, specialized infrastructure to operate. The entire ecosystem of commercial flight, booking systems, baggage handling, security screening, departure lounges, airline loyalty programs, is a superstructure built on the foundation that flying requires more resources than individuals can personally deploy. What happens to that superstructure when flying does not require more resources than individuals can personally deploy? The question is not hypothetical. It is the question that the cost compression trajectory of Chinese flying vehicle manufacturing is going to force the commercial aviation industry to answer within a time frame measured in years rather than decades. At $280,000, the Xpeng land aircraft carrier is already competitive with helicopter ownership for buyers who can afford either. At $140,000, which the cost compression trajectory suggests is achievable within the current decade, it becomes competitive with the fully loaded cost of multiple years of commercial aviation travel for frequent business travelers. At $70,000, it becomes a consumer purchase decision rather than a capital investment decision for upper-middle-class households in major markets. Each price threshold that the cost compression crosses opens a new buyer category and generates new production volume that drives further cost compression. The curve is self-accelerating in the same way the electric vehicle adoption curve was self-accelerating, slowly at first, then suddenly. The commercial aviation industry spent the past decade watching the electric vehicle industry disrupt automotive with a combination of disbelief and denial. It is now watching a version of the same disruption approaching from a direction it did not fully anticipate at a timeline it did not fully prepare for. The infrastructure side of the cost story deserves specific attention because it is where the cost compression has the most counterintuitive implications. One of the reasons flying has been expensive relative to driving is the infrastructure cost. Airports cost billions of dollars to build and require ongoing billions to operate. That cost is distributed across every ticket sold, making flight inherently more expensive per journey than ground transportation at the infrastructure level, regardless of fuel costs. Autonomous flying vehicles that take off and land vertically do not need airports, they need landing pads. A landing pad is a concrete surface with power connections and potentially a weather shelter. The cost differential between a landing pad and an airport is not measured in percentages, it is measured in orders of magnitude. A network of landing pads serving a metropolitan area costs a fraction of a single airport serving the same area. China is already building this infrastructure, not as a planned future investment, but as a present construction program running alongside the vehicle development. The landing pad network, the air corridor designation, the ground control infrastructure for managing autonomous flight at scale, all of it is being built now at costs that reflect Chinese construction economics rather than Western airport construction economics. When that infrastructure is operational at the scale the 100,000 vehicle projection assumes, the per-journey infrastructure cost of an autonomous flying vehicle trip will be a fraction of the per-journey infrastructure cost embedded in a commercial aviation ticket. That cost advantage compounds the vehicle cost advantage into a total cost of flying advantage that the commercial aviation industry has no obvious path to match. Now the honest part, because the cost compression story has genuine complications that the promotional version consistently omits. The price of the vehicle is one component of the cost of personal flight. Regulatory compliance is another. In most markets outside China, a personal flying vehicle cannot simply be purchased and operated without satisfying regulatory requirements that add cost and complexity to the total picture. In the United States, the FAA certification process for a new aircraft category can cost manufacturers tens of millions of dollars and take years. That cost is passed through to the buyer either directly in the vehicle price or indirectly through the higher operating costs that compliance requirements impose. The $4,937 Chinese vehicle cannot be imported and legally operated in the American market at anything close to its Chinese market price once the costs of meeting American regulatory requirements are factored in. This is not a permanent barrier. Regulatory frameworks evolve. The FAA is actively working on frameworks for advanced air mobility that will eventually create a pathway for vehicles like those China is producing to operate in American airspace under appropriate oversight. But the timeline for that evolution is years, not months. And the cost of compliance within that framework will add to the effective price of personal flight in the American market in ways that the Chinese domestic market price does not reflect. The infrastructure gap adds further cost complexity. A flying vehicle that cannot land anywhere useful is a vehicle that cannot be used usefully regardless of its purchase price. The landing pad network that China is building exists in China. Building an equivalent network in other markets requires investment, regulatory approval, and time that the vehicle manufacturing timeline does not wait for. The total cost of personal flight in a market where the infrastructure exists and the regulatory framework has been built is the price that the Chinese market is approaching. The total cost in a market where the infrastructure needs to be built and the regulatory framework needs to be created is higher by the cost of building those things, which is not zero. So here is the full picture of the cost compression story. The price of Chinese flying vehicles is falling. The trajectory is driven by manufacturing scale, learning curve effects, supply chain development, and the compounding advantages of a 30-plus company ecosystem improving simultaneously. The floor has not been reached. The curve is still declining, and the rate of decline is likely to accelerate as production volumes approach the thresholds where the nature of manufacturing changes rather than just the scale. The implications for commercial aviation are real, and the timeline is shorter than most industry analysis currently reflects. The cost advantage of personal autonomous flight relative to commercial aviation is not a future possibility. It is a present reality in China and an approaching reality in every market where infrastructure and regulation can be developed to support it. The complications are also real: regulatory compliance, infrastructure development, and the genuine engineering challenges of operating autonomous flying vehicles safely at scale in dense urban environments all add cost and time to the trajectory that the falling vehicle price alone does not account for. The honest summary is this: the price of a flying vehicle is falling faster than any Western aviation industry projection anticipated. The total cost of personal flight in a market with the full supporting ecosystem is approaching levels that will challenge commercial aviation's business model within a time frame measured in years. The total cost in markets where the supporting ecosystem does not yet exist is higher, and the timeline for when it becomes challenging is longer. China is building the supporting ecosystem. The rest of the world is deciding whether to build it. That decision and the pace at which it gets made will determine which version of this timeline the rest of the world experiences. The price is not the destination, it is the signal. And the signal is saying something that the commercial aviation industry cannot afford to keep not hearing. If this gave you a picture of where the flying car price story is actually going, that the headline version of it never did, hit the like button. It genuinely helps this reach more people who want the complete picture. Subscribe and turn on notifications because the next price milestone in this story is coming faster than the last one did. Drop a comment and tell me honestly, at what price point does a personal flying vehicle change your own transportation decisions?